task is to compute a power b optimally. So we have to give this task to the machine, and machine has to compute this one. So in a regular brute forcing approach, for computing a power b, we have to multiply a b times. So if you view this time complexity, we'll get O of b shell. So for example, there are cases when b is very, very large. For example, 2 power 10 power 6, then the time complexity of this calculation or computation will be 2 power 10 power 6 actually. So what we have to do is like we have to reduce this time complexity. So we have to make computation very easy. The optimal time complexity for computing a power b would be log b, O of log b. So for example, b is 10 power 6, and it would be nearly log 10 6. It will be 6 log 10, which is very, very less than 10 power 6. So how do we do that? It's a question. Then here let me take the example a power b. So the brute forcing method is a multiplied b times, but we can do something different this time. Firstly, we can divide this one into a power, I would say b can be divided into some c plus d. So c can be something, d can be something. So if we are dividing this one, we have to compute a power c separately, a power d separately. Then we can directly compute a power c into a power d to get a power b. This is a basic thing. So let me check whether b is odd or even. So if b is odd, then b minus 1 is even, and there will be separately one thing. So this one can be written as like a power b minus 1 by 2 whole square into a, if b is odd. If b is even, we can directly write b by 2 whole square. Why I am writing this one is key. I think we can instead of like directly computing a b times, we can instead compute I would say a square b minus 2 times, sorry, b by 2 times. Similarly, a power 4 b by 4 times. So by this approach, like a power b would be nearly some log b times or something. So let me write the algorithm. So function of a comma b. So if I would say if b percentage 2 equals to 0, it's even, then we have to return function of a comma, okay, sorry, I forgot this thing. If b equals to 0, we have to return 1. So if b is even, we have to return b by 2 star function a b by 2. So if b percentage 2 equals to 1, we still have to return function a b by 2 function a b by 2. Then we have to multiply this one by a. What this is doing is that it's calculating b by 2, a for b by 2, then we are multiplying by a. So by adding these terms, here it will be 1, then we'll get b. This one is a basic code for binary exponentiation with O of log b complexity. Then we can go to more interesting approaches in bits. So let me, for example, write b in bits format. So there would be some 0, 1, 0, 0, 1, 0, something. So depending on the bit, we can get our multiplication. For example, here a power b is there, so uh, this is a b, so I think we should multiply a power 0 one time, like 0 times, I would say. A power 1 one time, a power 2 0 times, a power 3 0 times, a power 4 one time, a power, I would say something, um, 5 6 one time. Because like what I am doing right now is key. I am dividing b with the help of binary approach. So I'm writing this one in this format, then in this format, then in this form. So these terms are separated terms. So why am I doing this approach? Because these things can be written in terms of two powers. So this one will be 2 power 2, this one will be 2 power 4, this one will be 2 power 5. So why am I still writing this one? I would say 2 power 3, so 2 power 4, something can be written as 2 power 2 into 2 power 2. So there's a complex calculation. There's not much complex, but it's very simple. There's simple yet complex calculation. So to get a power b, we are writing this approach. So like let me write this one as sigma of I is the bits position. Zeroth position is this one. This one is the index 0 position. So up to some infinity, until and unless we get something, until and unless we reach this part. So what is our task is sorry, a power, I would say 2 power I, a power 2 power I, sorry, a power I. Then we have to multiply this one with, okay, let me, sorry. So my task is here. So then what I have to do is like I have to add these things. So this one will be a power I. So next what we have to do is like we have to, okay, sorry, yeah, and here it would be I, sorry, it would be b of I. So what this thing makes is I b I. So it traverses to each of the blanks 0 1 2 3 4 5 6. So for example, here is a zeroth blank, so here we are getting 0. Then our task is to see b of I. B of I is the ith bit. So ith bit is 0. So here it will be 0, a power 0 0. So here it's a power 0 0. Then sorry, sigma. So then a task is to compute for 1. So 1th position, a power 1, b of 1 is 1. So it would be a of 1. So a power 0 multiplied by a of 1. Then coming to the second position, it would be still 0 because I is like b of I is 0. Then third, fourth. Let me go to the fourth one. So fourth position, a power 4 into 1 because b of 4 equals to 1. So here it would be a power 4. So a power 4 should be multiplied by a power 1. So what makes this special is the calculation which should be much easier. So computing of a power 4 or some a power 2 power I is much easier compared to this one regular approach. So let me give my algorithm. Function of a power p can be computed like let me take a result which is equals to 1. So I'm appending all my results in this result. So while I'm extracting the bits from this particular binary format. So while b is not equals to 0. So I have to check whether the ith blank is 0 or 1. So if okay, let me okay, there is regular a, so there is nothing to do. B and 1 equals to 1, then we can multiply the result by a. Okay, this a is dynamic. So for example, if we start a with some value, let me assume 3. It will not be 3 for throughout the code or throughout the algorithm. um, it would be dynamic, so it changes to 3 square, 3 power 4, 3 power 8, etc, etc. So okay, I think I forgot something. So let me, it would be 2 power I. Here it would be 2 power I, not a regular I, because it's a blank. So what I have to calculate is like 2 power zeros power, 2 power 1's power, 2 power 2's power. So it would be ideal to calculate that way. So then what I have to do is like a can be multiplied, a can be multiplied by itself. So we have to double the a because we are going to the next blank. So from 0th blank to first blank, we can multiply the a by itself. So here it would be a power 1, it would be a power 2, it would be a power 4, it would be a power 8, it would be a power 16, etc, etc. So what we know is like a power 2 power I plus 1 equals to a power I square. So using this approach here, I'm updating the values. So it will continue till b is not equals to 0. So what we have to do is like we have to get to the next blank. For example, uh, b is in the format 101. So in this case, one is being calculated. So here one is sorry, this blank is 1. So we are multiplying the result by a. So then we are going to the second one. We have to go to the second one. Here it would be 0, but still we have to update the a. So a would become a star a here. Then here it would be a power 4. So here it would be 1. So we have to multiply result by a power 4. So everything is nice, but we are not traveling in blanks or bits. So to travel in blanks or bits, we have to do right shift by 1. So after doing right shift by 1, this one would be eliminated and this one would be the next BR element, or next, I would say, least significant bit. In this format, like we can do binary exponentiation in O of log n time complexity, log d time complexity. This one is very helpful in many tasks. Binary exponentiation or its extracts can be very useful. Such approaches, like such examples, let me give one example. Okay, Fibonacci sequence can be used for binary exponentiation. So regular Fibonacci number is f of I plus 1 equals to f of I plus f of I minus 1. So this one can be calculated using matrix format. So let me assume this would be the format I minus 1, and this would be the f1 of I. This one's a vector with the two Fibonacci numbers. So we need a 2 into 2 matrix which calculates to give me f of I plus 1. So this row multiplied by this row should give me f of I. So I know that taking 0 here and 1 here will give me f of I, because this one will be multiplied by 0, this one will be multiplied by 1. So the result will be f of I. So f of I plus 1 can be written as f of I plus f of I minus 1. So we are having f of I minus 1, we are having f of I. So we have to multiply multiply and add with both of the term to get f of I plus 1. So let me take 1 1. So what happens here is f of I minus 1 is multiplied by 1, f of I is multiplied by 1, which are both added. In turn, we get f of I plus 1. So this task makes us calculate the next thing. So for example, f of I minus 1 would be the 0, f of 0, f of 1. So one transformation, matrix transformation uses f of 1 and f of. So for me, for example, I need I and I plus 1. So I need I transformations. So in regular method, let me take this as transformation matrix for Fibonacci sequence. So if I have to transform I times the f of 0 and f of 1, we'll get f of I and f of I plus 1. So if we are using a brute force approach, we are doing the transformation for f of 0, 1 some I times, which would be O of I complexity, and in turn it depends on I. If I is very large, the computation would be very large. So what we are using is a property of matrix where A into, I would say, A into B into C can be written as A into B into C. So instead of computing this computing transformation for vector each time, instead I would transform the transformation items. So the transformation items is a is similar to binary exponential process. So this one is very much similar to t of function of exponential function of t of f and I. So using the binary exponential format where I can be written in terms of bits, some 1 0 1 0, depending on the bit, we are multiplying t of f2 power I is the bit position in the bits index, and then multiplied by b of I of, sorry, I would assume this as b. So yeah, b of I, then b of I is 0, then it would be t of 0, b of I is 1, then we are multiplying by t of f into 2 power 2 of 2 power I. So another approach is like we have to check whether b is even or odd. Then we are like going to the recursion tree where when it's even, we are doing this for b minus b by 2. If it's odd, we are again doing for b by 2, adding t of f. So this is one such example. Another such example would be a permutation of a sequence. So let me take a permutation of a sequence. For example, there's a sequence 1 0. I would say not 1 2 3 is a sequence. So what is a permutation of sequence is that there is a permutation which would be given to us. I would assume the permutation would be 2, then would be 3, that would be 1. So what we have to do is like we have to shift the sequence depending on the permutation. Like let me shift this one. So for these, like for the sequence, like what I should do is like I should apply this permutation. So for this permutation, second term in the sequence is 2, then third term in the sequence is 3, then first term in the sequence is 1. So this one is a permutation of the given sequence. This is a very simple task, but the task becomes complex when we have to compute k permutations for the given sequence. That is, the given permutation should be calculated k times for the given sequence. So then here 1 2 3 the sequence, then 2 3 1 is the permutation. What happens here is that for the first permutation we are easily getting first permutation we are easily getting 2 3 1. This one is a new sequence right now. This one would be s of 1, this one would be s of 2, then we have to calculate s of 3. Like for now, like I'm just checking the permutations, I'm not doing anything different. So for this task, let me assume, sorry, so permutation should be applied to the given sequence. Then in the given sequence, second term is 3 right now, and then the given sequence, the third term is 1 right now, and the last term is 2. So 3 1 2, and fourth sequence will again go back to power 3. So this is a cycle, but there are times when it's very complex and does not give out a cycle. So still we have to compute the permutations k times. So for this case, like let me assume that permutation is a P sequence with S. So permutation k times will be P power k S time. So our task is to like let me assume a regular permutation would be P of function of Ps. This one should be calculated k times. This one is again a brute force approach which takes complexity of, I would say, k times. So to reduce the complexity and make the computation easier, what we have to do is that we have to again take the binary exponential format. So instead of permuting like s k times with p, we can follow another approach. Like this one works because like instead of like for example k is 2, instead of permuting a sequence 2 times, we can instead permute the permutation to 1 time, and then with the resulting permutation we can permute the sequence. So this one makes the approach very easy because like if we have to permute the permutation sequence of 4 times, we can do this one with the help of p power 2 and p power 2. P power 2 again calculation can be easy, p power p, and here p power p. So if we calculate p power p once, we can again use this here. It's a format of dynamic programming, but yeah, it's a binary exponential format. So if p power k should be calculated, which one would be very easy, binary exponential of p given k. Yeah. So the algorithm is same order even algorithm or bits manipulation algorithm. So this can be used to directly compute the sequence for p power k and s. So this one is one such approach, and also for transformation of a vector. Again, the transformation of a vector is T star V. Here is T is a transformation matrix n cross n cross m. Here V is a vector m cross 1. So it's a basic thing. But in my case, like the given transformation should be applied some k times. So it would be better to assume that n equals to m, because then in that case like m star m star m, like this one is like what should I say, like a matrix multiplication of a b b c will get ac. So again we to multiply with a here, the b and a should be same. So that's why I'm assuming that n and m should be same. So t power k v, it's very similar to the Fibonacci sequence. It's just that the number of I would say the rows and column numbers are changing here. Instead of 2 there is an n, remaining everything is same. Again, this transformation can be used for graphical approach where like I would say no, like I just firstly let me learn the graphical approach, then go to that part. For now I think that's it.